Hello, everyone, and welcome to today's webinar from Element 14 in collaboration with Texas Instruments. My name is Dave from Element 14, and I am going to be hosting the second part of a webinar series that we're doing with Texas Instruments and Worth Electronics. So today's presentation is about improving reliability in EMI behavior with low-power DC to DC converters. And today from Texas Instruments, we have Jürgen, who's going to be taking us through the presentation. So if you have any questions for Jürgen throughout today's presentation, you can ask him using the Q&A function of the WebEx application. We're going to welcome people to ask questions throughout the presentation, but we're going to reserve all those questions till the completion of the presentation, the last 15 minutes or so of the hour. So if you have any technical issues, you're having a hard time hearing or can't see the presentation, feel free to reach out to me via chat at Premier Farnell Webinars directly. Just wanted to let everyone else know that the recording of the first session of this webinar series is available in the Element 14 community. I'll be distributing some links at the end of the presentation for you to see that. In addition to the recording, we also have the registration pages for the remaining two sessions, so some great content yet to be had on the community. In addition to the presentation, we're also going to be giving away today a pocket reference guide to analog engineering from Texas Instruments. So we'll be distributing a link somewhere in the middle point of the presentation or towards the end, which will take you to a quiz. If you get those two questions right, then you'll be entered into a drawing for that pocket reference guide. Now, if you have already attended the first session and plan on attending the remaining few sessions, you'll also be receiving a certificate of completion for the webinar series, as well as the opportunity, if you answer the questions at the end of the quiz, for each of the webinar sessions, you'll be entered into a drawing for a power transfer solutions kit to go from Worth and Texas Instruments. So a lot of information there, but I would encourage you after the presentation to revisit the webinar page in which you registered from. Click on the live giveaway tab to read terms and conditions and all of the information. So without further ado, I'm going to turn it over to Jürgen, who's going to take us through a wonderful presentation. Jürgen, take it away.
Okay, welcome everybody to this webinar session, and special here to the second session, which is about improving reliability and EMI behavior of low-power DC-DC converters. Low-power DC-DC converters are typically very simple circuits, so all silicon or active circuitry is integrated in an IC, and they're only using a few external components, typically input capacitors, inductors, and output capacitors. So there's not much to do with circuit design, but there are some concerns or some items to address to get a reliable circuit, and a circuit which is behaving well regarding noise and EMI. So first part of this presentation is about component selection and PCB design. A typical DC-DC converter, or most of the DC-DC converters, are step-down converters as shown here, with the basic circuit consisting of a switch, of an active switch, which is S here in this example, a passive switch, which is drawn as a diode, and an inductor. There's an input capacitor and an output capacitor, but for the basic function of this circuit, to explain it, those capacitors are not really needed. The step-down converter operates in a way that the switch is open and closed, or closed in certain duty cycle of a fraction of the time period here. When the switch is closed, the input voltage is connected to the inductor and through the inductor to the output. Since the output voltage of a step-down converter is lower than input voltage, the inductor is charged, and what you can see here, the current in the inductor is ramping up. When the switch is open, opened, the current will be redirected because the inductor forces it to continue to flow. It will be redirected through the diode, and the inductor, the energy in the inductor is discharging to the output, which you can see with the downslope of the inductor current curve. This is all ideal behavior. What you can see in the switch current, it only carries current when the switch is on, of course, and immediately falls back to zero. The rectifier current or the diode current is zero, and when the switch is open, it takes over the current and it follows the inductor current. And when you look on the voltage across the switch, you have a very fast change in voltage when the switch is turned on and when the switch is turned off. This would all work well in an ideal implementation, but the real world has parasitics. So you have inductances in series to the switch. You have the connection to the input capacitor on the supply side and on the ground side. You have the connection between the switch and the diode or the rectifier at the switch node, and the rectifier to ground, and you have the connection to the output capacitor. As I already explained on the slide before, when the switch is open, the current changes fast, and current through the switch changes fast and through the diode. And when a current through an inductor, which is here marked as a parasitic inductance, changes fast, there will be a significant voltage which is proportional to the speed of the current change and to the magnitude of the current change. So we have critical conditions in this circuit regarding, or when we look on parasitics, is when the current is changing, and this happens when the switch is turned on, and it's even more severe because the current is higher when the switch is turned off and the diode is turned on, and at the end when the diode is turning off and the switch is turning on again. That's one part of the circuit, or one part of the problems parasitics can cause. There's also parasitic capacitance, and parasitic capacitance is critical when the voltage changes fast. And when you look on the switch voltage here, it changes fast, of course, when the switch is turning off and when it's turning on. If you look on the spectrum of trapezoidal waveform, you can see a high amplitude here, and at the pulse width or the frequency of this rectangular signal, which is underlying in this trapezoidal waveform, the amplitude is going down, and the switching or the edge of this trapezoidal waveform is the envelope is going down faster with -40 dB per decade at the corner frequency of this slope. You have the equation here and the graph here. So critical frequencies we have regarding EMI and noise are the switching frequency, of course, because this is how the converter operates, but as well, or in addition to that, the slopes at the switching transition of the current waveforms and of the voltage waveforms. So that's the theoretical part, which you just need to keep in mind for for the application examples or for the experiments I'm showing you in the following slides. So the test circuit I'm using is very simple. It's a completely integrated step-down converter, TPS62160 in this case, with a capacitor bank at the input and an inductor and a capacitor bank at the output. That's the basic configuration. I put in test points, so I have an SMA connector for measuring the noise or the ripple on the input voltage, same on the output voltage. And circuit here is configured to provide 5 volts, and the typical switching frequency of this device is in the range of 2 megahertz. The PCB layout examples I'm showing you are all using the same component placement, which you can see on this slide. So you see the capacitor bank on the input with the small capacitor C1 and the bigger ones, the 3 bigger ones going towards the input header here. The output capacitors are shown here, same structure, a small capacitor close to the IC, which is here, and a bigger capacitor if you move towards the plug at the output. The inductor is hard to see here, is just close to the IC. The first layout I'm showing here is a very simple layout. And also it's working well in these experiments. I would not recommend to do it this way, but I use it to compare to other layout versions. You see the routing, it's just done by using traces. For the power ground on the input, comes to the IC here. And for the supply voltage at the input, the inductor is connected here. And on the output side, it's connected to the output capacitors. The ground is, since it's intersecting with the signals on the top layer, is routed on the bottom layer, and for thermal reasons, a wider area has been used there. The PCB itself is a very simple PCB with 34 micrometer copper plating on top and on bottom, and a total thickness of 1 millimeter. And component assembly is only on top. The second layout example is almost the same as the first, but for routing the power, wider areas of copper are used. You can see the copper plane here and here for the ground, same on the output. The PCB is still the same, 1 millimeter thick with copper plating of 35 micrometer on top and on bottom. Version C is a very common practice of doing layouts in more complex systems. It's using routing on top, like it's shown in version B, and on bottom it's using copper fill as a ground plane and as a ground reference plane. So what you see in blue is covering the whole area, and it's connected to power ground on with all those vias. The PCB is still the same, so there's no difference in PCB cost, basically. Via technology is always the same here. Version D is using a more complex routing. It is routing the supply voltage on top with a wide area, and in the same geometry on bottom layer, it's routing the ground or the power ground. This way, the layout itself forms a capacitor with 2 plates, one on top and one on bottom, and a certain capacitance related to it. The board is still the same here, 1 millimeter thick and 2 layers. Version E is 4 layers, and it's a combination of version D with, I just switch back, with the routing of power ground and supply on top of each other with very similar geometry, and with shielding layers which are connected to ground on inner layer 2 and on bottom layer. So the thickness of the PCB is still the same. We're moving from a 2-layer to a 4-layer, and what we had with version D on 2 layers, top and bottom, is now on top and inner layer 1. This way we get the routing or the planes closer together. It's only 100 micron compared to 1 millimeter in the version D. So that's just to remember for the experiments and the measurement results afterwards. If you look on a capacitor, you can use, or you will use with such a circuit, you never get a real capacitor. So you want this, and you get this when you buy a capacitor. It has a mechanical shape or dimension, and this means it has inductance, and the material which connects the capacitor has resistance as well. In this switching frequency area, typically ceramic capacitors are used, and with this generic equivalence circuit, you get typical impedance charts which look like that. So you have an area where the capacitor is really capacitive, so with increasing frequency, its impedance goes down. There is a resonant point. Resonant is a series resonance between this capacitor here and the inductance of this capacitor. And above this resonance, you get inductive behavior or dominating inductive behavior. The resonance itself gives you an attenuated increase or decrease of the impedance here. So it's going down further than just than what you would see with just a linear decrease here and the intersection. If you look on the different shapes you can get, you have different sizes, very popular 1206 or 805 and so on. You can see when you look on data sheets that when you stick to a certain size of a capacitor, you always have the same inductance related to it. So when you increase capacitance, you're getting down here with the impedance, but you're not changing this area. And of course, for less capacitance, your resonant frequency moves up. If you change the geometry, here's a comparison of 1206 to 06 or 12, which basically has the terminals at the longer edge. You see a significant decrease in the series inductance of this capacitor, which may be beneficial for designing an input filter, or which definitely is, but those capacitors are more expensive. So what I explained briefly before, if you look on this picture here, if you decrease the size of the capacitor, your series inductance goes down, and if you just decrease capacitance, your inductance still stays the same. If you use a combination of different sizes, your impedance of the combined circuit is basically what is shown here with the yellow curve. So how to use that? The test set up here, you have seen the boards. The boards have been put at the same condition, same test condition to compare their behavior. They are connected with a lab power supply on the input. There's nothing in between, so there's no line impedance stabilization network as it is used with EMI measurements typically. There's electronic load at the output. The output voltage is set to 5 volts and the output current to 500 milliamps. There are different variants used in this test. The X1 or the one variant of the layout, so A1, B1, and so on, is with the C1 not assembled, and the 2 version is with C1 using a 470 picofarad with a 0402 package. C1, if I switch back to an earlier slide here, C1 is this capacitor which is closest to the input of the DC-DC converter. So when you look here, here's C1 and here's the IC, or first layout, this is C1. When you look on the switching node, and this is a measurement you do to assess the reliability of the circuit, you need to consider the highest frequency you want to measure. And since you have rise times in the range of a few nanoseconds, your frequency is in the range of several hundreds of megahertz. If you connect a probe as you buy it, usually with this crocodile clamp for ground and the tip for measuring the signal, you introduce a very big loop and a significant inductance in your probe connection. Probing like this does not really give you a good result, and in extremes you can destroy your circuit with that. So what you see on this picture here is a simple solution to fix this problem with a standard probe. So you just use a copper wire, wind it around the tip of the probe to connect the ground, and use the tip directly at the input capacitor. When you probe like that on the version A1, so that's the most simple layout I have shown you, you get a curve like that when you look on the rising edge on the switch node. So this is when the switch is turned on. You see an oscillation here with when you look on this cursor measurement here in the range of 400 megahertz. It's 368. And you see some overshoot. A1 has a capacitor C1 not assembled, and those measurements have been done to show the effect of the capacitor C1. If you look on impedance charts of different capacitors, here we show 2 different capacitors in 0402 size. It's a 4.7 nanofarad and a 470 picofarad, same size. You can see a self-resonant frequency for the bigger cap or the bigger capacitance here in the range of 100 megahertz, and here it is in the range of 400 megahertz. if you compare those at the critical frequency, which is 400 megahertz in this case, you can see that the impedance is in the range of 7 or 8, 0.7 or 0.8 ohms. And if you look here, you see that it's exactly at the self-resonant frequency, and you only have 0.3 or 0.4 ohms. So even this capacitor is the smaller capacitor. It's more efficient for decoupling close to the IC than the bigger capacitor here. And if you look on the switching edge, when you have this capacitor assembled with no layout change, you see a significant improvement and almost no overshoot anymore. So that's one of the key things to improve reliability of such a circuit, to avoid any ringing and overshoots. So the voltage stress on the switch node is significantly reduced, and there's less ringing in the circuit. In addition to that, if you look on the spectrum of the input voltage with a spectrum analyzer, while you do this experiment of probing the switch node, you can see a difference in the spectrum. This is when you have the probe attached. Yeah, you have a certain magnitude or certain level of noise. And when you look on this curve, this is just the same circuit, same operating condition, and the oscilloscope probe removed. You see a significant change here. This basically tells you that you have changed your circuit by measuring it, and your circuit is better when you're not measuring anything in this circuit. If you measure noise, and those are measurements on the output voltage, you can compare the spectrum of the output voltage here at a high frequency. Here the frequency goes from 100, around the center frequency of 350 megahertz with a span of 500, so you see a wide spectrum here. You can see again the impact of having this capacitor assembled. Without this capacitor, you have almost 10 dB more noise on your output as with adding this capacitor. And this is still the most simple layout I have shown you in the examples before. So this was the initial or the first version, the version A. And even in version A, you can improve the performance significantly by just using the right decoupling capacitor. If you compare the version A with the decoupling capacitor with the version C with the ground plane, you can see even if you're not assembling this capacitor, you're almost on the same level. If you compare to the 4-layer, so this is version A with the capacitor assembled, and version E, the 4-layer with the shielding layer, you can see even if you're not using the capacitor, you're getting a better result by just using this layout. And you still can improve by adding the capacitor. So this is without and with capacitor, and this is without and with capacitor. So you're in this setup, we're almost at the noise floor of the spectrum analyzer. You can do other measurements. For example, you scan the near field, so you scan radiated noise close to the PCB. Same comparison as I have shown before, version A1 with out capacitor and with capacitor. And here this is the area where the switching frequency is. So this is the switching frequency. You have the dominant pulse in the spectrum, and with the capacitor, you have a slight improvement here, even at the switching frequency and even using 470 picofarad for a 2 megahertz signal here. Here is the higher frequency spectrum. You have it's going from 100 megahertz to 1 gigahertz, and you see the improvement with the capacitor in the near field. Comparing the A layout with the C layout, even without the capacitor again, you see a significant improvement at the switching frequency. So we're going down by 20 dB or more than 20 dB at the switching frequency. And in this case, without the capacitor. And the higher frequency is looking very similar. Comparing to the 4-layer, you can see it looks like it's turned off. I checked this several times. There is nothing left anymore, and yeah, same with the higher frequency. So there's a significant improvement in radiated noise performance here. And yeah, it's still and always the same layer, same circuit. There's no change in the circuit. And even the capacitor, yeah, offers a slight improvement here. So this part is going down. When you scan the area, and this is a comparison between C1 and E1, using only one shielding layer or the ground plane was providing good results, as you have seen before, but around, when you look at the radiated signal around the IC, you still see some peaks. And when looking on the E1, there's almost nothing. Okay, so far, this was the PCB layout part. And now I'm showing an application example about, or showing how to power a noise-sensitive load. The applications example is a camera, a CMOS camera, which can be used in a car, for example, for ADAS applications. And this camera needs 3 rails, one for the analog and digital core and the I/O, so the logic in the camera. The power supply I've designed for that is using 3 times 62170, 3 times a step-down converter for all the sensitive rails and even for the analog rail, which is most sensitive in the camera. If you look on the circuit, it's very simple. Yeah, as I said, input capacitor, inductor, output capacitor, and a feedback divider to adjust the output voltage. This is done 3 times for the 3 different rails, and you can see the layout, which is very simple, and it's a small solution here. If you power the camera directly with default configuration of 62170, yeah, you see the result. This is not what you want, so you have a lot of noise in the picture. So, and if you look on the sensor, there's another experiment here. I'm powering all the rails with linear regulators from lab power supplies, and the most sensitive rail I'm looking into in more detail. I'm powering from a lab power supply, decoupling it with an inductor, and I use a signal generator for injecting noise in this node, and I'm measuring the spectrum of this signal in the following examples. picture is clean. There's not, no significant noise visible here. So if you look on the spectrum, we are powering the system with a linear regulated voltage, and we see a lot of signals here, or a lot of peaks in the spectrum. This is generated by the sensor, and it is related to the operation of the sensor. And when we look on the lower frequency part of it, you see a base frequency in the range of 12.5 kilohertz. And you see the harmonics of this frequency here. So if I inject noise, and if I do that between the spectral lines of the sensor, I can have a very high amplitude, and I don't see an effect. So the signal is still clean. When I move this noise into a spectral line, I see a significant interference. And this is also observed at higher frequencies. So we are here at, in the range of a megahertz. Between the lines, or the spectral lines of the sensor, the picture is good. And when I move into one of the spectral lines, I see the interference. And if I look on the power supply, if I use it in the default configuration, it is operated or operating in a light load operating condition, or what we call power safe mode. And in this power safe mode, the frequency is controlled by comparators detecting zero current. And what you can see when you look on the switching waveform is significant jitter on this waveform. If you look on this in a spectral or in a frequency domain, you see the peaks, which is the mean frequency here, and you see a white body here, which is caused by the jitter. If you recall the sensitivity of the sensor, with this white body, you definitely will interfere with one of the spectral lines, and this is what you see here. Okay, so what can you do? What I did here is moving the light load, transition to light load of this converter to a lower output current. And this has been done by just increasing the inductance. And if you look on the spectrum of in the sensitive area I have shown here, you're not seeing anything anymore because the switching frequency is just above it. Switching frequency itself is very stable and has a clear line here and not a white body. And if you connect this to the sensor, it's clean. So what I did is solving the problem without requiring any additional filtering circuits. So there's no ferrite bits, there's no linear regulators for additional filtering. It's just changing the configuration of the converter slightly and fixing the problem. So no increase in cost, not more components, just, I would say, doing it according to the load. And I think this was my last slide. Yeah, and I thank you for your attention.